So this is the recorded lecture for Chapter 9 in Physical Science. Whenever something moves, it's been pushed by a force over a distance, and we call this work. Raising a book, moving a pencil, moving my lips, walking around, I could name 1,000 things, some with great amount of work, some with almost none. We measure work by force times distance. This could be equal to the number of pounds times the number of feet moved. It could be equal to the number of newtons times the number of meters moved. The units will be Newton meters, and the name we give these units, the newtons times meters, is joules. So if we look at all kinds of work, it can be measured in joules, and that's the SI unit. What's important to us, though, is what causes work. There is actually something doing the work, and that's called energy. Take a car. There is a force on it that pushes it a certain distance. What does the work? Well, the gasoline was used to make fire. That fire was used to make heat. The heat was used to expand gas in the cylinders of the engine. And the work on the cylinder was used to move the wheels of the car. These are all forms of energy. Our lesson is that energy causes work to be done, and it can come in many different forms. Of all these forms, we will generally call the ones that store energy for our use potential energy, and those where there is something moving, kinetic energy. We can also trace the potential energy of the fuel back to other forms. Gasoline came from oil, which came from plants whose growth stores the energy of the sun. So ultimately, our cars are powered by the sun. In fact, any form of energy you can name can similarly be traced back to the sun. There is one exception to this rule, and I'll leave it to you to find the one exception to the rule. Thermal energy is important because we use it a lot. We keep our bodies warm by thermal energy. We drive our cars using thermal energy from burning gas. We heat our houses, make electricity from burning coal, and of course, the sunlight energy supplies the thermal energy that keeps the surface of the earth warm. We will think of thermal energy from now on as movement, kinetic energy of molecules, which we will see in chemistry are submicroscopic particles that make up all matter. Let's suppose I had a container with a golf ball in it to represent a molecule. As long as the temperature is above absolute zero, the molecule will move. So let's get the ball moving, and we can calculate the kinetic energy. Say it would be calculated by 1/2 mass times velocity squared. We'll see that if we put the mass and the velocity in, we'll come up with 0.025 joules of energy. Now let's put 9 more golf balls in there. As long as they are in contact, they will spread out the energy and all come to the same kinetic energy. So altogether, we have 0.025 joules times 10, the number of golf balls, which is now 0.25 joules. So now we have two properties of thermal energy that we are concerned with. One is the average kinetic energy. Here it would be the energy of the individual molecules, 0.025 joules. Then the total kinetic energy, which is the total energy of all the molecules added together, which is the 0.25 joules. No matter how many molecules we have, the average will stay the same, but the total energy will go up when we add more molecules. What we feel and measure as temperature, how hot and cold something is the average kinetic energy, and it's independent of how much stuff we have. What we measure as heat is the total kinetic energy, and it does change with how much we have. Let's look at temperature. We can't really tell the temperature by feeling things. You can see this if you put one hand in cold water and the other in hot water and then switch them both to lukewarm water. Both hands end up at the same temperature, but one feels it as hot and the other feels it as cold. You can try this if you'd like. Similarly, outside temperatures of 40 degrees Fahrenheit feels cold in July, but feels warm in January. What we can tell is when kinetic energy of the molecule is lower, we feel cold, and when it increases, we feel warmth. But we can actually measure the temperature. One way is by expansion of a liquid. Put a liquid in a bulb and heat it. It will expand, but usually not much. Still, if the expanded liquid is forced up a narrow tube, the height will go up with temperature, so we have a thermometer. The next question is what scale you put on the thermometer. Generally, you pick landmark temperatures for low, 0, and high, 100 degrees. In Fahrenheit, the low temperature is the temperature at which salt water freezes. You may be aware that if you put salt on icy sidewalks, it melts, and that salt on ice makes an ice cream maker very cold. Well, that's 0 degrees on the Fahrenheit scale. Fahrenheit then made the high value, 100 degrees Fahrenheit, body temperature, which we know is 98.6, but 100 is close enough. The Celsius scale places 0 at the freezing temperature of pure water, and the boiling temperature of pure water is 100. What I would like you to do is know the temperature of well-known situations on both scales. These are listed on the PowerPoint slide. So, for example, if I say you have body temperature of 39 degrees Celsius, you will know you have a fever. And if I say it's 30 degrees Celsius outside, you will know that it's a warm summer day. There is also one other scale of interest, the Kelvin scale. It was discovered when the volume of a gas, any gas, like air in a balloon, was seen to shrink as the temperature dropped, and the temperature where the volume became 0 was estimated from the trend in how it was shrinking. No matter what gas was used, the 0 volume temperature was always negative 273 degrees Celsius. This has become known as absolute zero because temperature only occurs when molecules move, and the only way for volume to go to 0 is if molecules stop moving. So negative 273 degrees Celsius is the lowest possible temperature. If there is a lowest possible temperature, then there should be a scale that starts at this temperature. That's what the Kelvin scale is. Absolute zero is 0 on the Kelvin scale, negative 273 on the Celsius scale. Other ways to measure temperature are with a thermistor. Two metals bound to each other in a strip will expand to different extents when heated and shrink when they cool. So the strip will bend away from the metal that expands the most when heated and bend toward that same metal when cooled. Another way to tell temperature is by color. We have all seen the glow of a campfire charcoal or a flame or molten lava. Well, once the temperature reaches about 800 degrees Celsius, the color changes from red to orange to yellow to white to blue as the temperature increases. This is called black body radiation, these colors, and can be used to tell the temperature of very hot things. Heat is a transfer of the kinetic energy, the total kinetic energy, not average. It is not temperature. Grab a metal and a wooden bar, and if they're sitting in the same space, in the same room, they will be the same temperature. But they don't feel it. And the question is why? Metal is an excellent conductor of heat. It's conducting heat away from you. Wood is a poor conductor of heat. It doesn't conduct heat away from you. There are many units used to measure heat. The one we used in the lab was calorie. This is the amount of heat needed to raise the temperature of a gram of water 1 degree Celsius. It is convenient because it is so easy to heat up water and weigh it and find its temperature change like we did in the lab. Kilocalories uses the metric prefix kilo, which always means 1,000. So 1 kilocalorie equals 1,000 calories. That means any amount of calories will be equal to 1/1000th the number of kilocalories. A capital C calorie is also a kilocalorie. That's a unit used on most food packaging. You may remember how confusing it was when half a peanut had 500 small c calories in the lab, but you were used to thinking in small c calories, but they are only 1/1000th the size of a capital C calorie. So it was really only 0.5 capital C calories. We can also use joules. This is the SI unit, and it can be found by multiplying calories by 4.184. So what's specific heat capacity? It is a measure of how much heat something can hold. Imagine you had a swimming pool filled with 2,000 kilograms of water, and next to it a car made of 2,000 kilograms of steel, both outside on a hot sunny day. Now you take identical twin children and you put one in the car and the other in the swimming pool, and you leave them there the whole day. The swimming pool child is fine, but you would never put a child in a car all day. When it was hot outside, it will heat up very hot. It all has to do with specific heat. Water has a high specific heat, so it will soak up a lot of the heat energy before its temperature rises. Steel, however, has a low specific heat, so it will soak up very little heat and gives it away easily, which causes a great increase in temperature. There are many examples of differences in specific heat, and they often involve water. For example, suppose you bake a pie and it comes out of the oven too hot to eat, but after 5 minutes you break off some crust and find that it's cool enough to eat, so you take a big bite of the pie and you burn your tongue. Well, the pie filling had a high specific heat, so it was going to take a long time to lose enough heat to cool, while the crust had a low specific heat, so it cooled very quickly. Other water effects: if you go to Chicago on a hot summer day, it will often be much cooler by the lake because the cold water takes much longer to warm up than the land. Its high specific heat means it will have to soak up a lot of heat before it warms up. On the other hand, in the winter, the lake is warmer than the land because it takes so long to draw enough heat out to cool it down. Oftentimes, water in the ocean will warm up in the region by the equator and then follow ocean currents to a colder northern region. The high specific heat of water will not allow enough heat to be removed to cool down before it gets north. In this way, several coastal regions in the north stay much warmer than their counterparts on land. This includes Seattle, Washington, the Alaskan coast, and the British Isles. In the last part of your chapter, they review some of the things that we've already looked at and bring to your attention that they're due to thermal expansion, such as changes in bridges, sidewalks, and railroad tracks, the thermistor expanding, the thermometer bulb, air currents expanding. That gives rise to winds going across the world, and the ocean currents, as I just measured. The other one is the strange behavior of water. It turns out that water floats because of expansion due to lack of thermal energy. When it freezes, it actually expands, and that causes it to float. Almost stranger than that is that water will actually shrink as it gets colder and sink to the bottom of the lake as it gets colder in the fall. But a curious thing is 4 degrees before it reaches freezing, water actually starts expanding again. So the density of water is most dense at 4 degrees, but on its way towards 0 in freezing, it actually gets less dense, a very strange effect, and that keeps the 4-degree water at the bottom of lakes and then the other water that eventually freezes at the top of lakes.